This is the 18th video in our series on Lie algebras, and here we're going to explore more about roots and root spaces. So let's fix some notation for the day. So we'll let L be a finite dimensional semi-simple Lie algebra over C. We'll let H be a Cartan subalgebra of L. Recall that we defined what that was previously. We'll set this capital Phi equal to the set of roots. So in other words, it's the elements of the dual space of H that are non-zero as maps, and the L alphas, their root spaces, are also non-zero, where let's recall the L alpha, the root space of alpha, is going to be all x in L, such that if you bracket H with x, you get alpha evaluated at H times x for all alpha in H. Recall that alpha is an H star, so what it does is it takes inputs from H and it gives you complex numbers. That's why this makes sense here. And then given this setup, we can have the root space decomposition of L with respect to the Cartan subalgebra as H plus the direct sum of all of these L alphas as alpha goes over all of the roots. Now we're going to start with a definition, and that is of a root string through beta, an alpha root string, I should say. So let's suppose that beta is either a root or beta is equal to 0. And I guess I should say here that alpha is also fixed to be a root. Then the root string, the alpha root string through beta, is defined as follows. So it's going to be the sum over, well, all beta plus C alpha in phi, as long as C is a complex number, of this L beta plus C alpha. So it's going to be a direct sum of all, or of a certain subset of these root spaces. Okay. So let's maybe start with our first result of the day, and that is that this root string is in fact an SL alpha module. Remember, from any root alpha, you can create this thing that we called SL alpha before, which was a copy of SL2 based around this alpha. Okay, so let's maybe take this SL alpha to be equal to the span of H alpha, E alpha, and F alpha. So, well, where are these things living? So H alpha is inside the Cartan subalgebra, E alpha is inside of L alpha, and then F alpha is inside of L minus alpha. So that's like based around something that we did before. Okay, so now let's say if we've got an X in one of these spaces right here, we want to make sure that if we hit it with anything from SL alpha, we land back, well, maybe not in one of these spaces, or not in the space that we started with, but inside of M. Okay, so let's suppose that X comes from L beta plus C alpha. And notice that that's going to be, well, it's a component of M. Okay, so now let's do the calculation. So let's notice that if we do H with X, oh, I guess I should be doing H alpha with X, then what are we going to get here? Well, we're going to get beta evaluated at this H alpha times X, but notice that that's in this same space. This is this L beta plus C alpha, which is one of the components of M. That's just based off of how elements of the Cartan subalgebra will interact with things from these root spaces. Okay, so now let's look at E alpha. So if we do E alpha with X, where do we end up with? But now we can't really determine where this is unless we bracket it with something from H, just recalling what it takes to be inside of one of these root spaces. So let's do that. So in other words, we're going to do the bracket of H with E alpha X. But we're going to start by using the Jacobi identity to decompose this into two parts. So let's observe that we can decompose this into the bracket of H with E alpha and then X, and then plus E alpha bracketed with the bracket of H with X. So again, that's by the Jacobi identity. But now we know how to handle this bracket of h with e alpha as well as this bracket of h with x. Given up here that we know that e alpha is in L alpha, and here we know that x is inside of L beta plus c alpha. So let's see, this guy right here will give us alpha h, and then that'll be multiplied by the bracket of e alpha with x, where I took that constant out. And then for this next bit, again taking the constant out, we'll have beta plus c alpha applied to h, and then the bracket of e alpha with x. And so putting this all together, observe that we have beta plus c plus 1 times alpha applied to h, and then the bracket of e alpha with x. But notice what that tells us is that the bracket of e alpha with x is indeed inside of this L beta plus c plus 1 alpha, which again is one of the components of M. Now you can do a really similar calculation to show that if you do the bracket of f alpha with h, you'll get something inside of L, let's see, it'll be beta plus c minus 1 alpha, which is again one of the components of M. So any way you slice it, if you bracket an element from SL alpha with an element from M, you get back inside of M. But that's exactly what we needed for M to be one of these SL alpha submodules. Okay, let's move on. Let's look at a couple of examples of these root strings. So let's consider SL3, which has roots plus minus alpha 1, plus minus alpha 2, and plus minus alpha 1 plus alpha 2, where we've previously looked at some examples with SL3 and used this notation. So if we look at L alpha 1 plus L alpha 1 plus alpha 2, this is the alpha 2 root string through alpha 1. And it's going to be spanned by this E alpha 1, E alpha 1 plus alpha 2, where again we had that in a previous video. Then we've got this L minus alpha 2 plus L minus alpha 1 minus alpha 2. That'll be the minus alpha 1 root string through alpha 2. And then finally another example will be this L minus alpha 1. Then the one-dimensional subspace spanned by H alpha 1, and then L alpha 1. So that'll be the alpha 1 root string through 0. Notice that's a copy of SL alpha 1, the SL2 subalgebra kind of generated by the root alpha 1. Okay, let's look at our next result. Okay, so our next result says that if we've got a root alpha, then the dimension of its root space, L alpha, is 1. So that's a pretty strong result. It tells us even more about this decomposition over here. And then the next part of this result is that if C alpha is a root, then C is plus minus 1. So in other words, like 2 alpha cannot be a root, for instance. Or even like 3/4 alpha, that can't be a root. Now previously we proved that if alpha is a root, then minus alpha is also a root. So this kind of turns that into an if and only if statement. Okay, so now let's get on with the proof. Okay, so let's notice that if C alpha is a root here, then what do we have? So then for an X in LC alpha, we have the following, just based off of the definition of LC alpha. So if we take the bracket of H with X, where H is from the Cartan subalgebra, we're gonna get, let's see, C times alpha H times X, and this is gonna be for all H inside of H. So that's just the map C times alpha, or really C times the map alpha acting on H. So in particular, what do we have? Well, we have H alpha on X will be equal to, let's see, C alpha H alpha times X. But we know what alpha acting on H alpha is, just based on the fact that that forms like an SL2 triple arrangement, and we know that that's going to be 2. So this gives us 2 times C times X. But then we also know that eigenvalues of the bracket of h alpha with something are in z. They're integers. So again, that's something that we proved previously. But what does that tell us? Notice that the eigenvalue here is 2 times c. We showed earlier, like I said, that the eigenvalues are in z, but that means that 2 times c must be an integer. But what does that tell us? That tells us that c is either an integer or c is a so-called half integer. So it's in the integers plus 1/2. Okay. So next up, let's consider the root string of alpha through 0. So that's going to be m, which is equal to h, and then the direct sum over all c alpha, which are roots of L c alpha. So again, that's the alpha root string through 0. This is the 0 part, and then, well, that's the kind of bigger and smaller alpha parts. So recall that we had this alpha root string through 0, which was denoted by, well, it was this h plus the direct sum over all c alpha, which were roots of L c alpha. And now we're going to look at the following claim. So maybe it's more of an observation, and that is that the kernel of alpha direct sum with SL alpha, that copy of SL2 built out of alpha, well, notice that that's naturally a subspace of M. Notice that the E alpha is in L alpha, the F alpha is in L minus alpha, those are both parts of this, and then the H alpha will be inside of H. And then the kernel of alpha is inside of H as well, given that alpha is in H star. So it maps from H to C. But if it maps from H to C, then the kernel has to be, well, part of the domain, which is H. Anyway, so that's why we know that this is at least a vector subspace of M. Now we're going to show that it's also a submodule with respect to this SL alpha. And how do we do that? Well, if we take elements from SL alpha, and then we hit them with things from SL alpha, we're going to land back in that SL alpha because that closes a subalgebra. But that means that we all only need to consider elements from the kernel of alpha and make sure that they're not moved anywhere else. So let's do that. So let's take x inside of, like I said, the kernel of alpha, which also, like I said, is a subset or a subspace of H. And now let's look at the bracket of H alpha with x. So now let's observe that that's going to be equal to 0. That's because both of those are inside of H, which is an abelian subalgebra. That's part of the definition of the Cartan subalgebra. Okay, so H alpha does not take x outside of this space. Now let's maybe look at E alpha with x. But notice for E alpha with x, we can write that as minus the bracket of x with E alpha. But then x is inside of H, E alpha is inside of L alpha, so we can use that kind of root space behavior to give us minus alpha of x times E alpha. But then x is inside of the kernel of alpha, so alpha x is 0, giving us 0 here. Which again means that E alpha does not move x outside of this space right here. And then maybe I'll just write similarly here, as it's pretty much the same calculation. If you take the bracket of F alpha with x, you also get 0. Okay, but that's exactly what we needed to show that this is a submodule. Okay, so let's maybe look at another little observation, and this will have to do with the dimension of the kernel of alpha. Okay, so let's observe that alpha is going to go from H to C. Okay, but then we also know that alpha is not 0, and we know that alpha is not the 0 map because, well, it was a root, and roots can't be the 0 map by this rule right here. Okay, but what does that mean? Well, if it's not the 0 map, then the image of alpha has to be 1 because it maps at least to some non-zero element of C. But then by the rank nullity theorem, what do we know? we know that the dimension of the kernel of alpha has to be the dimension of H, the dimension of the image of alpha. I missed a dimension here, which was 1. So now we know that the dimension of the kernel is, well, it's almost all of H. It's only missing one vector, and well, actually the vector that it's missing has got to be H alpha, because we know alpha acting on H alpha is 2, kind of by the construction of the SL2 triple. So anyway, what we have here is that H will decompose into the kernel of alpha, and then let's see, plus, one-dimensional vector space spanned by H alpha. Okay, so far we took this root string, and well, what did we do? We showed that the kernel of alpha plus SL alpha was a submodule of this root string. And then we also showed that the kernel of alpha had, well, codimension 1 with all of H. And that allowed us to do this decomposition of H with the kernel of alpha plus, well, a one-dimensional subspace spanned by H alpha. Okay, now where are we going to go from here? So given the fact M itself is an SL alpha module, and this kernel alpha plus SL alpha is a submodule of this module, what does that mean? Well, that means that we can take M and we can decompose it as the kernel of alpha plus SL alpha, and then plus, well, whatever else is left over. So let's maybe just point out that this W is what's left over. And then I guess the claim here is that W is equal to 0. So here I'll put 1 to show that W is 0. In other words, well, there's nothing left over. And then, well, once we show that there's nothing left over, we'll see how that leads to the two conclusions of our proposition. Okay, and we're going to prove this by way of contradiction. So by way of contradiction, let's suppose that W is non-zero. But notice that W is also an SL alpha module. It's like the complement of this submodule that we had. So since it's an SL alpha module, which is isomorphic to SL2, then that means it can be decomposed into irreducibles by what we saw about the representation theory of SL2. So that means that, well, we can find irreducible or a simple SL2 module inside of W. That's going to be the first case here. So, or maybe like that'll build our two cases. And so first I'll say there is an irreducible SL2, which is isomorphic to SL alpha submodule VD of W. And here I'm going to take D to be odd, such that D is equal to 2k plus 1. In other words, D is odd. But then let's write VD, which is D plus 1 dimensional. In other words, it's 2k plus 2 dimensional via the appropriate H alpha eigenvectors. So here we're going to write this as the span of, well, what do we have here? We're going to have V minus D, which is really like minus 2k minus 1. And then that's all the way up to V minus 3, V minus 1, V1, V3, all the way up to VD. So if you count carefully, that kind of obviously has 2k plus 2 total vectors. And then, well, recall the shape here. So I'm going to lay out this visually. So I'm going to have a V1 here, or maybe that's a V minus 1 here. And then we'll have a V1 here, and we'll have a V minus 3 here, and a V3 here, and then that's going to go on and on and on. Well, it's going to end at some point. It'll end at this VD and this V minus D, but we won't put those on there. And then, well, let's maybe put some boxes around these so we can see what's going on. And then color code the action. So let's say that the action of H alpha is in blue. The action of E alpha is in this magenta color. And then finally, the action of F alpha is in this green color. And recall what happens here is that H alpha just doesn't move between these, spaces. So it takes V1 to itself multiplied by an eigenvalue of 1. V minus 1 to itself multiplied by an eigenvalue of minus 1. Similarly, eigenvalue of minus 3 here and positive 3 there. And then that extends on. And then let's see, the E alphas move us up the chain. And then at the top, it'll move us to 0, as we saw earlier. And then the F alphas move us down the chain like that. Great. And now, well, from this, we can look at the following kind of observation. And that's if we take H alpha with V1, well, we're going to get V1, which is the same thing as 1/2 times 2 times V1, which is the same thing as 1/2 times alpha applied to H alpha, given that alpha applied to H alpha is 2, times V1. But then that's equal to the map alpha over 2 applied to H alpha applied to V1, or multiplied into V1. But then also we know that V1 is inside of M. But M has this decomposition up here. But then that means it has to be inside of one of these because we did not get 0 as an eigenvalue. We got something non-zero. So it's got to be inside of one of these, but given this relationship right here, it's got to be in the space with root alpha over 2. In other words, it's in the L alpha over 2. In particular, we have alpha over 2 is a root. Okay, so let's see where that takes us. Okay, so let's see what we've seen so far. From this leftover bit W, we had this first case, and that was there was an irreducible submodule VD of W where D was odd. But that led us to seeing that alpha over 2 was a root. So in other words, we had alpha and alpha over 2 both roots of this algebra. Okay, but what does that tell us? That means that we have 2 copies of SL2 triples. Well, 2 at least. We have this H alpha, E alpha, and F alpha, and we have the ones based off of the other root. Because remember that we get an SL2 triple from any root that we have. So in other words, we've got like H alpha over 2, E alpha over 2, and then F alpha over 2. Okay, but now what we'll do is we'll take an X from an appropriately chosen root space. In this case, it'll be L alpha, and then we're going to notice the following calculation. So let's do the bracket of H alpha over 2 with X. But now let's observe that that's going to be alpha applied to H alpha over 2 times X, just given the fact that X was in L alpha. But now I'm going to write that as 2 times the map alpha over 2 applied to H alpha over 2 times X. Just like using the fact that 2 over 2 is 1. But now we know that this alpha over 2 applied to H alpha over 2 is equal to 2. That's because if you take any root and you apply it to the H sub that root, you always get 2, based off the fact that these were SL2 triples. But that gives us 4 times X. Okay, great. But now we're going to re-decompose our original module up here, M. And we're going to decompose it like this. We're going to decompose it as the kernel of alpha over 2, which I guess is kind of obviously equal to the kernel of alpha, plus SL alpha over 2, plus W prime. And then under this setup, observe that X must come from W prime. So we'll just note here that X must come from W prime, but notice that X has an eigenvalue of 4 from H alpha over 2. So if we're assuming that W prime is an SL alpha over 2 module, well, this fact that we've got an even eigenvalue, what that means is that there is a V maybe I'll call it D prime, which is a subalgebra or a submodule of W prime, where D prime is even. Okay, now let's see where that takes us. Okay, so let's see what we've done so far. We took this M and we decomposed it 3 different ways. And one of those ways arrived at this assumption that we had that if there was an irreducible SL alpha submodule VD of W where D was odd, then that implied that alpha and alpha over 2 were both roots. But then that gave us this other decomposition, and from that we were able to show that there must exist a VD prime where that's another simple SL, in this case alpha over 2 submodule of W prime, but in this case D prime was even. So in other words, if we've got one of these odd irreducible representations, then that means that that implies that we can build another decomposition and get an even irreducible subrepresentation of that decomposition. Okay, so now let's take the basis of this VD prime. Recall that that's going to look like V minus D all the way up, V minus 2, V0, V2, all the way up VD. So it's D prime, that should be prime, plus 1 dimensional. Okay, great. And then it has like kind of a similar picture to what we had before. So let's put our VD prime here. We'll have our V minus 2, our V0, our V2 in the middle, and then our VD prime way off to the side. And this should have a minus attached to it. Okay, so now let's put some boxes around those so we can kind of see what's going on. And then we'll color code the action just like we did before. So let's say this blue is H alpha over 2 action. And then this magenta is E alpha over 2 action. And then finally, this green is F alpha over 2 action. So the F alpha over 2 will move us down the line, finally getting at the end where it turns into 0. The H alpha over 2 acts with eigenvalues. So here we've got 0, 2, we've got minus 2. Over here we have D prime, and way over here we have minus D prime. And then the E alpha over 2 will move us up the line. So that'll move us from 1 to the other, and then finally at the very end, it moves us to 0. So something like that. That's the picture at this moment. But then let's look at this and observe that just the evenness of D prime means there's this vector V0 that, well, it really gets mapped to 0 under this H alpha over 2. But where does that put this V0? That means that this V0 must be inside of H. That's just given this decomposition here. Okay, so, well, what does that tell us? Well, that means that we can do the following calculation. We can do H alpha over 2 with V0, and we'll see that we get C alpha applied to H alpha over 2 applied to V0. But then also we can take this H and we can decompose it the way that we did before. So that was as the kernel of, let's see, alpha over 2 plus this one-dimensional subspace spanned by H alpha over 2. But that's going to be a subspace of the kernel of alpha over 2, and then plus this SL alpha over 2. Okay, and then, well, that's, by some stuff that we discussed earlier. But now, this is a problem here, because notice that V0 comes from this VD prime, which is a subset of W prime. But then here, we showed that it also came from this portion. But those things are complements of each other. They don't intersect at all. So that gives us our contradiction, given that V0 cannot exist in those 2 places. So again, we did that by just like playing these multiple decompositions of M off of each other. Okay, but anyway, what did we end up contradicting? Well, we ended up contradicting something that we assumed at the very, very beginning was that W was non-zero, but that means that W must be equal to 0. But since W is equal to 0, we have an easier decomposition of this M. So now let's see how that simpler decomposition finally leads us to our two conclusions. Okay, so we just spent a long time showing that our M had this decomposition of the kernel of alpha direct sum with this SL2 subalgebra SL alpha. But notice that we know how to write SL alpha. And in fact, what this tells us is that we have the kernel of alpha. And now this is going to be as vector subspaces, not as submodules. So as vector subspaces, this is the kernel of alpha, direct sum with CH alpha, direct sum with CE alpha, direct sum with CF alpha. So those are just the basis vectors for SL alpha. But now earlier we argued that this stuff turned into H. And then, well, we know that E alpha is inside of L alpha. So this is direct sum with L alpha, direct sum with L minus alpha, because we know that F alpha is inside of L minus alpha. So anyway, in the end, well, what we see is that this L alpha is exactly this one-dimensional subspace E alpha, and we see that this L alpha minus alpha is the one-dimensional subspace CF alpha. So that shows us that each of these is one-dimensional. Also, notice that inside of this decomposition, you don't see a multiple of alpha other than plus or minus 1, and that's the second part of the result. So a result of that previous proposition is the following kind of natural decomposition of our Lie algebra L. First of all, it has a basis given by the basis of the Cartan subalgebra union these vectors, which I'll call X alpha, where alpha ranges over all of the roots. And that's because recall that these L alphas were one-dimensional, so we'll just say that they're spanned by each of these X alphas. Now that means that we can write L as H direct sum with the direct sum of all of these. These should be a CX alpha here, so those are all like one-dimensional subspaces. And then I should also point out that we often split up our roots into positive roots and negative roots. And then we set X alpha, where alpha is a positive root, equal to E alpha, and X minus alpha equal to F alpha, where E alpha and F alpha form two parts of a SL2 triple. And then we've got this nice decomposition of L into all of these F alpha terms. And then kind of in the middle is the Cartan subalgebra. And then over on the positive side, if you will, is all of the E alpha type terms. So notice that all of the H alphas are going to live inside of H, but I'm not writing that as a direct sum of maybe the one-dimensional subspaces built by the H alphas. That's because those are not generally linearly independent. And we saw that in the SL3 case. Recall that we had roots alpha 1, alpha 2, and alpha 1 plus alpha 2, and their negatives. But for the Cartan subalgebra, it was only two-dimensional. It wasn't three-dimensional. Okay, so now let's finish off with one more proposition. Okay, so here's our last result of the day. So let's suppose that we've got two roots, alpha and beta, and then beta is not equal to plus minus alpha. Then we've got three results. So first of all, there exists non-negative integers r and q such that for integers k, beta plus k alpha is a root if and only if k is between minus r and q. So that means that we've got a root string, if you will, for instance, beta minus 2 alpha, beta minus alpha, beta, beta plus alpha, beta plus 2 alpha, beta plus 3 alpha. Maybe that could be our range of the root string. Notice that means that you can't have any gaps, if you will. Okay, and then furthermore, we have beta evaluated at h alpha is r minus q. So that's maybe the relation between a couple of these ideas. So this h alpha is, well, the Cartan part of the SL2 triple from alpha. And then next up is this pink dot result, which says that if alpha plus beta is a root, then the bracket of E alpha with E beta is non-zero, and it's a constant multiple of E alpha plus beta. And then finally, beta minus beta evaluated at H alpha times alpha is a root. So notice that this is simply a number times a root. So that's going to be like a combination of roots. Okay, so let's get into it. So we're going to first consider the root string of alpha through beta. So let's write it like this. So we've got the sum over all k of L sub beta plus k alpha. So in other words, like I said, this is the root string of alpha through beta. Now, previously, maybe not today, but we showed that this is an irreducible SL alpha module. Okay, but then as an SL alpha module, if it's irreducible, well, what does that mean? That means that this M is isomorphic to VD for some D which is non-negative. Recall that that was like our classification of SL2 modules. And remember, SL alpha is isomorphic to SL2. Now the idea is we're going to play the decomposition we have here as a root string and the decomposition we know about these VD modules off of each other. Okay, so let's see how to do that. So let's notice that beta plus k alpha is a root implies that L beta plus k alpha is equal to, well, it's non-zero. But if we know if it's non-zero, it's got to be one-dimensional. So I'll say that it's spanned by this vector that I'll call x beta plus k alpha. Now I want to look at how h alpha acts on that to get an idea for where it would lie inside of the string or the chain of vectors that builds this VD. So we'll look at h alpha, acting on x beta plus k alpha, and that's via the adjoint action. Now, via a very simple calculation, this is going to give us beta acting on h alpha plus 2k times the original vector, x beta plus k alpha. Okay, great. And now let's color code the SL alpha action like we've done a couple times already in this video. So let's say that H alpha acts with this blue thing, E alpha acts with this magenta, and F alpha acts with this green. And then, well, what we have, because we know that VD has a lowest weight vector and a highest weight vector, and VD is spanned by vectors of this form x beta plus k alpha, well, we'll just pick the numbers r and q to produce those lowest weight vectors and the highest weight vectors. So in other words, we'll have something like this. X beta minus r alpha will be our lowest weight vector. And then way over here, this x beta plus q alpha will be our highest weight vector. And then, of course, we're going to have some vectors in between as well. Like this vector here will be x beta minus, let's see, it'll be r minus 1 times alpha. So that's really like r alpha plus another alpha. And then maybe right before this would be x beta plus q minus 1 alpha. Okay, so then how does this kind of thing go? So let's put some boxes around those, and let's see. The E alphas will bring us up this line. And then after getting past the highest weight vector, we'll get 0. The F alphas bring us down this line, and after getting past the lowest weight vector, we get 0. And then, of course, the H alphas, well, they act just exactly like we have seen here. So they're going to act on this with this sort of eigenvalue right here. So this will be beta of h alpha plus 2 times q. But then over here, this is going to act as beta acting on h alpha minus 2 times r. Great. But then also, we know that these VDs are like kind of symmetric, right? So this eigenvalue over here should be the negative of this eigenvalue over here. But then that allows us to set up an equation. We have negative this eigenvalue must be equal to that eigenvalue. In other words, negative beta of h alpha plus 2r must be equal to beta of h alpha plus 2q. But then we can move some things around there and pretty easily solve for beta applied to h alpha. And we'll see that beta applied to h alpha is indeed, well, this number that we were going for here, r minus q. Okay, so we got our value for beta minus h alpha. I guess I should point out here that this is definitely an integer. So, well, that takeaway says that any root applied to an h alpha will always give us an integer. So that's kind of interesting. And then, well, how do we get the rest of this? That for all k in z, this beta plus k alpha is a root. Well, that's because by the structure of this highest weight module, this VD, we know that we don't miss anything in the middle here. There aren't any gaps, if you will. And so that means that, well, this thing down here is a root and so on and so forth. Okay, so we proved this blue dot. Now let's move on to this pink dot. Okay, so we have our m up here just for reference. And so now we're going to prove this by contrapositive. So if the bracket of E alpha with E beta is 0, I should say, then what that tells us is that E beta is a highest weight vector of M. But if that's the highest weight vector for M, then L alpha plus beta is 0. Oh, but what does that mean? Well, that means that alpha plus beta is not a root. Okay, so that proves the non-zero-ness of this statement. But then how do we know that we're going to get a constant multiple of E alpha plus beta? Well, that follows from the fact that each of the root spaces is one-dimensional. Okay, so that's good. That finishes this pink dot. And now we can actually just quickly move on to this green dot. So let's maybe note the following. So we're going to do beta minus beta evaluated at h alpha times alpha. So we know beta evaluated at h alpha, that's this r minus q. So that's going to give us beta minus, then we have r minus q times alpha. But then observe that we can rewrite that as beta plus q minus r times alpha. But now let's observe that that's most definitely going to be a root, and that's because the number q minus r, well, it lives between these two numbers minus r and q, just kind of naturally. Oh, and that should have been a non-strict inequality, which we saw during the proof, but I just had a typo up there. Okay, so just to reiterate, we know that this is a root because our q minus r lies between minus r and q. Okay, so that finishes the proof of this proposition, and I think that's going to be enough for this video, so we'll pick it up next with the next video.